the chronic responses, or what happens after we become acclimatized to the cold. Okay, so here are our two main objectives. And really the second one deals with acclimatization for the most part. Bergmans and Allen's rule, not as much, but you'll understand here in just a second. So many zoological studies have been done by what are called comparative physiologists. They're some of my favorite people in the world. They don't really like to argue anything. They just try and understand challenges that people have by using animals. Okay, so they study a certain type of goose to understand how a goose can survive hypoxia, to apply that to us. Basically, any challenge that a human experiences, they have the opinion that there's an animal out there somewhere that has adapted to survive this challenge. So whether it's being on top of Mount Everest, living somewhere where it's really hot, that sort of thing. And so in doing these zoological studies, there was a guy named Bergman, and he came up with his rule. And what he found is that individuals in cold environments have large body mass. Really what it is they have decreased surface area to mass ratio. Okay, so these are like short, stocky individuals. Allen's rule is kind of the opposite. And so Allen's rule is looking at things from a warm environment. And what he found is that individuals that live in warm climates generally have long appendages, and this increases the surface area so they can lose heat. Okay, so Bergman's rule, short, stocky individuals. Allen's rule, tall and lanky. Okay, but the reason that this has happened is because one wants to conserve heat and one wants to get rid of heat. And so over time, this is kind of evolutionary stuff. This is how a lot of these cultures have developed. Okay, and so I want to take a minute and just look at things from kind of a zoological perspective. There's a couple animals that I want to talk about here. So we've got an Arctic fox. It's a small animal. Generally, small animals struggle to live in the cold, but the Arctic fox does all right. And it has a high surface area to volume ratio. But one of the things that helps it is it's got this thick fur, which insulates. And this insulation is key because it reduces the effect of the wind. Now, we haven't talked about the wind, and we're really not going to talk about it very much. But I just want to give you a little bit of an idea. So as we give off heat, doesn't matter the environment that we're in, we actually create a microclimate just above the surface of our skin. Okay, in the cold, this helps us to maintain a little bit of heat. The wind, though, breaks that insulative layer up, and that's where the wind chill comes from. Okay, and so the wind chill makes it a lot easier to lose heat. If you're in 0 degrees Fahrenheit weather and there's no wind, as opposed to 0 degrees Fahrenheit weather with a 20-mile-an-hour wind, there is a much greater heat loss with that windy condition because it breaks up that insulation, and so it's easier to lose heat. And so animals that have this thick fur, that reduces that effect of the wind. And then we've got emperor penguins. We've probably all seen, or most of us have seen, March of the Penguins. They live in, arguably the harshest climate on Earth, right? They get down to Antarctica, they lay an egg, they sit there, and they just, I don't even know. But they survive these harsh winters. The way they do this is through strength in numbers, okay? Birds are warm-blooded, but it gets so cold in Antarctica that they don't have a high enough metabolism to sustain their body temperature. And they're a little bit higher than us. So what they do is they get into groups of thousands, okay? And if you have seen March of the Penguins and you've watched it, if you remember, they have like a time-lapse photography thing where they go through and show how this whole colony rotates. And so the birds that are at the outside eventually get to the inside. Those that are in the inside eventually get to the outside. And so what they're doing is they're reducing the surface area, which reduces the amount of heat that's lost by the group as a whole. And so they're able to conserve body heat. Now, when it comes to humans, one of the most common ways that we talk about acclimatization to the cold is through something called Young's model. Okay, and so in order for Young's model to kick in, we have to experience chronic or repeated cold stress. And there's one of three things that ultimately happen. So we go through this little flow chart, and the first one is, well, am I losing body heat? If the answer is no, then that means you're experiencing something called cold habituation. So cold habituation, or just habituation, means you have a reduced or a dampened or a desensitized response to a stimuli, okay? And so if we're talking about cold habituation, well, what's the normal response when you get cold? You shiver, so you have blunted shivering. And then the other thing that happens is you don't vasoconstrict as much because you're not losing the heat, right? So if we come back to this, you're not losing body heat, and so that allows you to have a little bit more increased skin blood flow. You're not shivering. Your body's just kind of adjusted to be able to maintain its temperature. However, there are many situations where you're not able to maintain body heat, and so then you ask the second question, and then based on the yes or no, you're doing one of two things. Is your increased metabolic production in the cold, is that sufficient to defend or maintain body temperature? If it's yes, then we say you're experiencing metabolic acclimatization. Okay, and with metabolic acclimatization, there's two parts. You've heard of the first one. It's shivering. So shivering thermogenesis, that means you're generating heat by shivering, right? Those involuntary muscle contractions. They don't let you move. They don't let you wander all over the place or whatever, but they're, those involuntary twitches that if you're shivering while you exercise will make exercise very difficult. But the purpose isn't for movement. The purpose is to release heat. Then you've also got something, or potentially have something called enhanced non-shivering thermogenesis. So this is generating heat by mechanisms that aren't shivering. This is through the activation of something called brown fat. Now, most of us don't have brown fat. Infants have brown fat. It goes away as they get a little bit older. And then people that live in really, really cold climates and work in really, really cold climates, they maintain brown fat. So this is like lumberjacks in Scandinavia, okay, or up in Siberia, that sort of thing. All right. Basically, what brown fat does is it takes, remember the electron transport chain. So the electron transport chain does its thing, but instead of forming ATP at the end, all that energy that's used to form ATP is just released as heat. Okay, and as a result, you don't have any muscle contraction, which is good because that muscle contraction requires some energy. And so instead, it's all going to heat production. And so because you're not shivering, you don't have those involuntary muscle contractions. That's why we call it non-shivering thermogenesis. Now, most of us won't experience this, don't have this, but some people do. And so another thing that also happens is that we move our metabolism so that we're using fats. We're breaking down fats as opposed to carbs. So we hold on to our carbohydrate stores. Okay. Now, if we come back to this flow chart and the answer is no, I'm not increasing heat production through metabolic processes, then I've got what's called insulative acclimatization. Okay. And so insulative acclimatization, again, has two primary components. The first one is we have more vasoconstriction. Okay, that means blood's going to go to the core. Now, the second thing that happens, and it sounds bad, is that if I've got a lot of heat in my core, I've increased the gradient between the core and the skin. Okay, big gradients mean it's easier for heat to move and to be lost. That's not great, but because I have that increased vasoconstriction, the fact that I have this increased gradient prevents me, or the fact that I have the vasoconstriction prevents me from having that extra heat loss. And so with that, that's where we're going to end on these chronic responses to the cold.